Hi, this is our report for second computational experiment. Firstly, I would like to define the problem. We are interested in studying how wave scattering depends on obstacle size. We use FDTD to numerically simulate it. The size of our numerical domain is 20 wavelengths by 20 wavelengths. This works as Maxwell's equations are scale invariant. The resolution that we choose is 40, which just means that our domain gets spatially discretized into 40 steps along each dimension. Equivalently, the grid size in FDT would be zero point 0.5 by zero point 0.5 wavelength. The time step is chosen as per the Courant factor. In this domain, we place a thin perfectly metal sheet at the middle and choose a frequency of 1 unit, which just means that the source emits waves of wavelength 1. Finally, we need to put an absorbing boundary condition around our domain which ensures that no waves are reflected from the boundary. This is achieved by using perfectly matched layers of thickness 1 wavelength. We start the simulations with a small obstacle of size 0.5 wavelengths. This is a regime when wave propagation is essentially unaffected by the obstacle size, as it is much smaller as compared to the wavelength. This is at 1.2 wavelengths, and still we observe that wave propagation is more or less unaffected. At 2 wavelengths, we begin to see some region where there is no wave, but there is still significant diffraction. This is the second regime of wave scattering. At 3.2 wavelengths, we observe that there is little diffraction while the linear propagation starts to become more apparent. Finally, with a large obstacle of 10 wavelengths, there is no diffraction. And we also observe interference between incident and reflected waves. This is the third regime of wave scattering, and you can observe a distinct shadow region and linear propagation of the wave. This is our code. We change the parameter obstacle size to control for the height of the obstacle. We set up the source and PML as we have already shown in the previous figure. We run the simulation for 150 time steps, which is enough to converge at the correct solution. And to summarize, we would say that the wave essentially bends around the obstacle when it is much smaller than the wavelength. When it is of comparable size, say 2 wavelengths, we observe diffraction in the shadow region. And with much larger obstacles around 3.2 wavelengths or more, the obstacle effectively shadows the wave and there is linear propagation. The diffraction effect decreases as the obstacle size grows in relation to the wavelength of incident light. If you have any questions, do let us know in the comments, and thanks for watching this video.